Hi there, RStudio friends. It's Jordy again, and welcome back to my YouTube series slash mini series, where we go through different things that we can do in RStudio. And in previous weeks, the last couple of videos anyway, we did some linear modeling, and these were pretty simple models where we had a linear relationship, or thought we had a linear relationship between predictors and the response. One thing potentially that was kind of lacking from all of that was visualizations. And when it comes to big data sets, often we want to find relationships, potential relationships between lots of different columns or lots of different variables. And that might be because, at least in my field, we had data on, in oceanography, we had data on the environment and we had data on animals. And we wanted to see how these different columns or variables interacted with each other. What did they have in common? Were there kind of any underlying relationships between the columns? And we wanted to visualize those interactions or relationships. And that's where visualizations of all of this via things like NMDS, dendrograms, comes in very useful. Now, note that I am mostly talking about ecology and oceanography here in terms of my experience with this. However, you could use multivariate analysis, NMDS, dendrograms, for so many different purposes. I was recently thinking about how it could be used in terms of data on populations of countries paired with data on the economy of countries, or anything really, data on behavior of patients together with morphological measurements of the patients. So different kinds of data, seeing how they overlap. And that's what we're going to focus on today. And there's probably lots of different libraries in which you can kind of do this sort of thing. Maybe you've been recommended one by people you know, a supervisor or a colleague. The one that I'm most familiar with is Vegan, Vegan library. But like I said, it does things like NMDS and dendrograms and things that you can probably also make in other libraries. So notice in my packages, if I search for vegan here, I've got this one already. It says community ecology package. And then if I just go into Google and search for vegan R, we get more. Yeah, this always seems to happen. I just love when we're working in coding how you search for stuff and it gives a totally different answer about cars and stuff. But we'll go to the GitHub where we can get more information about this. Okay, and it talks about ordination. Okay. So what this is relating to is it makes a graph. You can make a graph with data colored by different colors and different symbols, for example, that correspond to stations, correspond to different samples. And you can see look at the distance between the points on the graph. And that will tell you information about how samples or stations are related. Okay, a more colorful ordination plot where sites are points and species are text. Okay, this looks like it's using base R for this one. You can also use ggplot for the graph, after using vegan to actually make your similarity matrix, and we'll talk more about that in a minute. So here you've got different stations, I believe, in the blue words, And you can see that certain stations that are close together on the graph might be more related in terms of, whatever they're containing, probably species, versus ones that are further away on the graph. So this gets down to similarity and dissimilarity between samples. So now back to R. Just prior to moving on to vegan, I wanted to reiterate something from a previous session. I sometimes use base R for various things, okay? And you'll remember base R has certain symbols that it uses, such as the $ for when you refer to a column, and square brackets. Square brackets often are used for when you are creating a new data set that takes out certain row numbers especially, and column numbers. Let's see how we can easily use the square bracket method for cleaning in terms of reducing size of data frames in base R. Okay, so let's start with the iris one, the iris dataset, and I go to this simply because it's pretty short. It's a small data frame of 150 rows. Data's data, and this one, yep, you remember, information on flowers. Now, imagine firstly we want to take out the sepal length column from this. I will of course make a copy of that and turn it into iris2 based on iris. Fix my camera here. And without using any complex pipe function stuff, we can just use square brackets here. If we just do -1, we'll run this and then view the iris2. The new data frame that we created, and you see that that's a very quick way to take out a column by the number of the column. Okay, so that has deleted the sepal length column. People often have issues, as have I in the past, about commas within this square bracket code. Okay, so this works the same as putting a comma in front of this, okay? Yep. And you can also check that by seeing down here, retained the same number of rows, 150 rows, no rows have been touched, but we've got 4 columns in contrast to 5 columns that were in the original and 150 rows. So some people have issues with the comma, and that makes sense because if you put the comma after the -1 instead of before the -1, it has a very different effect. I'm sure you can guess what that effect is. Instead of taking out 1 column now, 5 columns remain, but there are 149 rows because the row index number 1 has been taken out. So that is taking out rows instead of columns. Taking out columns, and this one is also taking out columns. When it comes to taking out rows, you can also do this. You can do -C here. Put a C in front of the numbers of rows you want to take out, and we can take out multiple rows at the same time. So we're taking out rows 1, 2, and 3 from this. And so I should probably just call this one iris4. Note that I'm constantly making new data frames when big changes are made, such as removing stuff. That's important so you don't overwrite the original. It now only shows from a minimum of index 4, 1, 2, and 3 being taken out. And I guess the reason why I'm getting into that now is because the square bracket stuff is commonly used in fact, a lot of base R is still commonly used in vegan. So you need to have a kind of understanding of how the square brackets and the comma thing works. So now vegan. And we'll make sure we've loaded this. If you don't have it, you're going to need to get it through the packages or install.packages code. At this point, I have not made a data frame that we would want to use yet, so that's what I'm going to do now, and I'm just going to go into Excel for this. So here is not one that I made earlier, it's a data frame that I made just now. I paused the video, I went into Excel, and I created an imaginary data frame that could be used for the purpose of the kind of multivariate analysis that we want to do in vegan. And this imaginary data frame includes fake numbers on counts of different species of animals. So these could be count data of different creatures such as fish, dog, bear. The numbers along the top correspond to the station number and the sample number. So this is station 1, this is station 2, this is station 3. Note these stations might be in very different places. This is all imaginary. The number before the dot is the station number, and the number after the dot is the sample number. So 0.1, 0.2, 0.3 correspond to replicates that might have been taken at that place. And the numbers might not make a lot of sense. I made them off the top of my head, but you can see that from this already we have numbers that range from 0 to about 200 or something close to that, 142, 189. Okay, so then, as you know from a previous session, we're going to save this and we're going to put it into a CSV file. Okay, we can go browse here. Then we can go into YouTube, that's the YouTube folder. I'll change this to CSV instead of Excel, and I'll just call it data. Great. So now we want to read that data in. Remember that with file names, we need to include the .csv part at the end and put it in quotation marks. You might also notice at this point that the font in my script source panel is bigger. I just changed the font through the global options, which is really useful because you might find color schemes, editor themes and fonts that you really like. View data. Okay, great. So this data is now brought in. Incidentally, this is a good point to introduce the concept of putting the species column as the row names. We can do that because this column contains entirely unique values. The name of any animal is only given once, and so these values are unique. For the purpose of the graphs we're trying to make, it helps to have them in the row names. It also allows us to do an analysis prior to using vegan, such as pairs panels, psych library, pairs panels, pairs, and also core, the correlation heat map. All of these require your columns to just be entirely numeric data, but they can allow you to visualize relationships between them. And it's often the way that I start looking at data in order to see what relationships exist between columns. So I'll just do that now. So we'll create a copy of data, call it data2, then the pipe function. So I'm using a combination of pipe function and base R these days. The code for this is column to row names. Okay. Sorry, my mouse doesn't seem to be working very well, but I'm just going to start typing it. And then you just write the name of the column that needs to get put into the row names, which is the species column. It could also be done by the number. Here, I think it doesn't necessarily matter if you put this column in quotation marks or not. Quotation marks would have to be used if you had any columns that have spaces in them, but we don't have that. So we now view the data 2, and then we'll try the pairs. Yeah, now they're here. And that's incidentally how the empty cars data frame was created before. Putting the car names in the row names instead of row numbers. So we'll try pairs here to make a graph of this, because we can do that now very easily. It would have been possible to do it before, but we would have just had to use square brackets to decide which columns could go into the pairs graph, as this has to be entirely numerical. This aesthetics can be improved by doing upper panel equals null, which I discussed before. And then we have this. So note then that we would have to add color to this, color to these points to specify the different animals. But that's not what we're going to focus on today. What we're going to focus on today is turning this into a format for making a dendrogram and making an NMDS plot. Okay, so we'll do that first, and then I'll talk more about what your dendrogram and NMDS plot can show you. So note that when we did the pivoting before, we wanted to take the names of these columns, sepal length to petal length, and stack them in a single column, okay, as in a column that was called parameter or feature, okay, and then put all the numbers that are currently under these titles into another column. So we'd have a much longer data frame with fewer columns, putting all of this information into one, okay, and the information that would not be included in that column would be species, okay? So species would not be included in the stacked feature column. And to do that, you would you'd work with code like this. Let's call it iris long is based on iris pipe function pivot underscore longer. You're going to specify here the numerical data columns, okay? Calls equals 1 to 4. That excludes species. And then you have, let's do names underscore 2. Okay, this is generally going to be feature, okay? So the title that would describe well all your sepal and petal morphometrics. Okay, and then values 2 can just be values. That's your actual data. Okay, or we can call it data. So let's have a look at the new data frame that was created. Yeah, so that's done what we wanted now. It's put all the features into one column. The species have been retained in a separate column, and your data, the values that corresponded to each of these, are in their third column. Now you can use pivot wider as well, but I've had problems with pivot wider before because it can actually cause some issues, especially for big data sets and where you have lots of different groups. So in a scenario where we wanted to pivot wider, looking back at So pivot underscore longer is quite straightforward. You can pretty much copy and paste that code for all kinds of different data sets where you have this common situation of different features, different morphometric measurements being in their own columns. In a scenario like this, we could imagine now that we would want to pivot wider instead. So we would want to put these species names along the top, and therefore would have the sample IDs, the station samples, to be here instead. And that would require kind of like transpose. Let's call it transpose for that kind of change. Now we can do that, and it's easier to transpose if we use old base R code. Okay, so transpose longer or transpose data so that the first column is put as the column titles. Yeah, so what we're trying to do, the ultimate goal, is to take this column with the animal names, put those entries along the top where the sample IDs are, and put the sample IDs where the animal names are currently. So this code is a little technical, but hopefully if we space it out into individual rows, it should be easier to follow. And we can do like data T, which stands for transposed, is back arrow set names, okay, as dot data frame. So it's like set column names as dot data frame. This is going to try and close it after, sorry, my mouse is giving me problems today. As dot data frame, I'll get a new mouse at some point. It's going to try and close it with a closing bracket. We don't want to do that. We want to put it onto a new line, okay, and then you want to have T, okay, data in the inner brackets, then the square brackets like we saw before, and we're going to do comma -1. Now you remember that the comma before refers to columns, so we know that we're working with columns. We're going to take out the first column and we're going to replace it with the column names as they currently stand. Okay, so we're going to switch them over, and so you got to put a comma there, and then another one which is just data with no bracket in front, and then comma 1. So let's see if we close all this, make sure we close it with a pink bracket. That's why the color scheme helps. And run it. Well, it appeared to work because we don't have any error. So now just let me view this data frame here, the new data we've created, data underscore T. And this is what we want. So it worked very well, and it worked easier in my opinion, at least from my experience, than pivot underscore wider does. It's actually just taken exactly the column headings as they were, which are the sample IDs, and it's put them straight into the row names, and that's good for what we're trying to do. It makes it easier to graph, and it also means that all of this data is in the columns remains numeric. So the next thing, and at this point, just for transparency, we could copy and paste the code that we ran before, the pairs, and try it on this and see what the new graph looks like on the transposed data. Yeah, so you see this change that's been made, and it allows us to ask different kinds of questions now. Allows us to see, over all the samples and all the stations, what's the relationship between fish and dog and fish and bear and fish and bird? And when it comes to population dynamics, that could actually be really interesting, because we might expect that as the number of wolves go up, then that might have some effect on the number of lynx, or certainly the number of cats, you know. Depends what your question is, what your project is, but that gives some options there for exploring different questions. Remember that we haven't used colour yet to signify, in this case, different samples. We could do that as well if you are interested in that. Now, the pairs plot isn't part of vegan. What we're about to do now with dendrograms and NDMS is part of vegan. And what this allows us to do is to really explore similarity between samples. Really similarity between whatever you've set here as your row names. If we then go into Google, okay, and I'm just searching for vegan dendrograms R, we can understand a little bit more about how this works. So you kind of make a tree of life almost with this dendrogram. And there's a couple of important aspects here. The first thing is clusters are formed in the diagram, and these are clusters of samples that are similar to each other. These samples form one chunk, okay, or one cluster, okay, 7, 3, 5, and 6, which is quite different to this cluster that's over here that contains 24 and 11. Note that the actual position of the samples on the x-axis is not too important. What's much more important is which samples form specific clusters, and also the length of the lines here, which are like the branches of the tree. So the shorter the lines, the more similar the samples are to each other in the cluster. Now that suggests that, for example, these ones here, 24 and 11, are quite similar to each other. Okay, all of these kind of have similar lengths in the lower branch, but you also need to pay attention to the branches above them. And somewhere up here would be like the common ancestor, if you start looking at animals. This can also be used for the genetic stuff you see online with ancestry and finding out who's related to who. So that's what dendrograms are used for. And NMDS shows the same kind of results but in a different way. So in a graph that looks like this, you should see the same kind of results with samples that are close together, being close together, that are similar, being close together on the graph across axes which are ordination axes, NMDS1 and NMDS2. Again, the position of these points or samples on the axis is not so important. It's more which samples are related to each other that's important. Now, this NMDS allows you to add multiple information to the graph. So instead of just having, it's a bit difficult to read this, but it's basically the circle corresponds to what is referred to here as BM type, and the triangle refers to supertype. These will be features of the various samples. And then on top of that, they've added information about the time of day that the samples were collected, whether early or late. So in this case, information about the environment was also added onto this graph. So you can get a good idea about how samples are related using both dendrograms and NMDS. Like I said, the dendrogram and the NMDS should show a lot of similarity, but you can also add extra information about the environment or about other aspects, maybe population size of a country, onto an NMDS graph by using different colours or different shapes of the symbols. So let's give this a go for our data now and do a dendrogram. But first, what needs to happen is we need to create what's called a VEG dist, right? A similarity matrix. I won't spend too much time today talking about all the maths and equations behind this and about different similarity measurements, indices. But we could make another video about that, or you can contact me about that separately. There's lots of information about it online. For now, what we can do is we can create something called a VEG dist, okay? And I'll call this similarity matrix. This back arrow of VEG dist data underscore t. So we use this data frame here. Okay. If we now view that similarity matrix, let's see what happens. Okay, so you get all these numbers here. So a little explanation about the numbers that we're seeing here. These are the Bray-Curtis similarity metric, and as you can see, it's like a table, a tabulation of each sample against each other sample. Now, where these values are 1, that means that the samples are very different than each other, completely different, and if they're 0, they're completely identical. So let's just search a little bit on that in Google, and you see the same information here. Quantifies how different two ecological samples are based on species abundance in this case, ranging from 0 identical to 1 completely different, calculated by summing absolute abundance differences and dividing by total abundances. Its popularity in ecology for biodiversity analysis is popular for that purpose, but is technically a dissimilarity because it doesn't always satisfy the triangle inequality, unlike a true distance. So other metrics are used for specific purposes, such as Euclidean distance method or metric. So now going back to the dendrogram, making a dendrogram for this, we're now ready to do a H-clust. So we're going to just do plot H-clust, then the name of that similarity matrix. Similarity, sorry, I spelt it wrong there. Okay, here we go. So this shows us, according to these random numbers that I made up, okay, that there might be samples which are closely related to each other and ones that are not closely related to each other. There is no rhyme or reason for why this would be the case, considering I made the numbers up. But for theoretical education, it looks like these ones, sample 2.1, 2.3, form one cluster. 1.2, 2.2 form another cluster, and these are incredibly separate than these samples here. You can also, we don't have it here, but you can also get a sample that's called superfluous, which means it's unrelated to all the other samples. It's in its own cluster, okay? It's in a cluster entirely on its own. We don't see that here, but there'll be examples of that on the internet. Now let's present this in a different way using the NMDS. And there's a couple of things we need to do here. We need to create a scores data frame. So we're going to use NMDS scores, which are going to go along the two axes, the NMDS1 and the NMDS2. Okay, and so scores data frame is going to be created simply by as.data.frame meta MDS. Okay, meta MDS brackets similarity matrix. Let's run this. Okay, we're missing something here, which is we forgot to put scores in front of the meta NMDS. Okay, that should have worked now. And we'll view this. Okay, now we have the two axes that we're interested in, NMDS1 and NMDS2, with the sample IDs being the row names. By plotting this, we can put it onto, a common scatter plot with two axes, and we can compare the results of that to the results of the dendrogram. So I can make a ggplot here. And we'll present the results in a couple of different ways. Firstly, in terms of plotting with the sample IDs shown as text on the plot, and another case where we have the sample IDs shown as colours on the plot. But prior to doing that, we need to get the sample IDs out of the row names. It's easier to work with. It can be done with them being in the row names, but it's easier to work with when those sample IDs are in a column. And so we'll reverse what we did earlier, where we put the column to the row names, and we'll put the row names to the column. Let me then make a copy of the scores df and call it scores df2. It's based on scores df. Pipe function, row names to column. Here we go. There is an option there for row ID to column, but don't click that. We want row names because they are non-numerical. Column. And then here we write what the new name of the name of the new column is going to be. Okay, scores df is based on, sorry, I missed out the underscore there. Okay, so that's now hopefully taken the sample IDs and put them into a column called sample, and we'll just check that that worked. View our scores underscore df2. Yes, it has worked now. So we've got everything we need now to make a ggplot, which will be an NMDS plot, because it's going to have this as the x-axis and this as the y-axis. Make a ggplot. We'll start with the method where the sample column is given different colors on the graph. And as I said, we would set up our ggplot in the same way as we have previously. Scores df underscore df2. AES corresponds to what we're going to set as our axis. X equals NMDS1, Y equals NMDS2, and then col equals sample. Okay, then let's do a geom point for that, and let's increase the size of the points so we can see them a little bit better. by putting size equals 2 here. When I run this, the graph should appear here. Well, I think that's a bit overkill. So size 10 for this. And now you have a nice graph. The color thing kind of makes it actually a little bit confusing, so maybe not the best solution here. But it would probably be nicer if we have them all be in the same color but use text on the graph to show the different samples, or to emphasize the different samples. So let's do that. And for that, I'm not sure if I've already shown you guys this, but we would take this part out here. We would need a couple of things now. Okay, so we're going to need a geom point, and we're going to need a geom text repel. Geom text repel. Geom text is also possible, but the geom text repel stops the text, the labels, we're going to create labels here, stops the labels from overlapping the points, which makes it easier to understand and to read. Okay, that needs a library called ggRepel if you're going to use this geom text repel. Okay, I'm going to change a couple of things here. I'm going to cut this out of the first line. Okay, so just leave the ggplot line empty. Put this here, that will then make the same graph as we already have, well, without the color. Okay, and then exactly paste this here. So same stuff in both lines for now, and then we add a label in here. Okay, label equals sample. So 3 lines, one for the ggplot itself, which will give us our axes, or a basic graph. Okay, and then the geom point adds the points, the circles, and the geom text repel adds the labels. Okay, let me also change the size here to what we had before in the geom point line. Now notice that that has then also got rid of our legend, because or the legend for the samples, because we don't have any colors anymore. So this is a useful way to visualize which samples form specific clusters, and you could go further by plotting cluster circles around the samples. But if we are to compare this then with the similarity the dendrogram that we made earlier, we should see some crossover there. We said before that 2.1 and 2.3 were similar. 2.1 and 2.3 are over here. We said 1.2 and 2.2 were similar, and 1.2 and 2, they're over here. And then all the other ones, 1.1, 3.3, 3.1 and 1.3 are all over on this side. So ordination has definitely shown that these there's different clusters going on here, and as I said, the position of the specific samples on the graph is less important, but we know which samples are more similar in terms of, in this case, the animals, the counts of the animals that are present there, the wolves, the dogs, the cats, etc. And so this can be very, very useful for finding out samples that are similar and samples which are dissimilar. Now, what we didn't do here is add environmental data or population data or or other data which you might have onto the graph, and that can be done quite easily through ggplot, simply by making use of the different visualizations that you can add in a ggplot. For example, we could have had shape equals temperature, and as long as we have temperature data in a column here, we would be able to assign different shapes, triangles, circles to temperatures, etc., etc. And size can be useful, shape can be useful. You could also use facet wrap if you wanted for another column, for example pH data. Different levels of pH would be given, presented in different panels in a facet wrap. So you would just have to add the extra data that you have that correspond to the different samples to this scores data frame, and that would solve that problem for you and allow you to show lots of information in the same plot. So I hope that was helpful. Let me know what you want to work on next time, and I hope you have a great week. Bye.